Alrighty, welcome to day 6 in your planners. You can be writing down day 6 or page 42 to 43. Remember, we also got problem set that you can be working on, which will be due on our review day. So you have 2 warm-up questions. Sometimes it's easiest to do these on a grid. We had on the bottom of page 34 in our packet some spare grids that we use just for kind of scratch work. So you can use one of the grids there if you would like to help you out. And for question 2, that one was usually easiest just knowing the rule. So if you need to look back in your notes, page 5 at the bottom would be a good spot to look for that. So we'll give you maybe 4 minutes to see if you can have your homework out, do the warm up, and then we will go over that. So for the first one, x equals -1. If you're unsure of what the line x equals -1 looks like, pick a couple points that have x values of -1, like -1, 0, -1, 1, -1, 2. And that will give you your line of x equals -1 after you plot a couple of those. Our point A was 4, -5. And we just want to find A prime. We want to reflect over that x equals -1. Most reflections, if you've got a vertical or horizontal line, easiest to just count and see how far you are away. Go the same distance on the other side. So we are 1, 2, 3, 4, 5 away from our line x equals -1. Go 1, 2, 3, 4, 5 away on the other side. So this is A prime. We just got to figure out its coordinates. Well, from the origin, we went left 1, 2, 3, 4, 5, 6. So we're going to have A prime has an x value of -6. And then we went down 5. So we will have -5. For y equals x, our rule is all you do is you just switch the x and y. So in this case, A prime would just be -5, 4. If you were to do that one visually, y equals x is the line where all the x's and y's are the same. So like 0, 0, 1, 1, 2, 2, 3, 3, and so on. So there's roughly our line y equals x. Our a, which was for -5, would be here. And because we have a line with a slope of 1, we would want to count at a slope of -1 to see how far to get there. So that would be 1, 2, 3, 4, 5 diagonals going through. 1, 2, 3, 4, 5 going the other way. This would be our A prime. So then we have our -5, 4. That's a bit tricky to do, so that's why knowing the rule for y equals x can be helpful. Alrighty, going over to the homework. Some of these we did in class. So we plotted both our sets of points. And if you notice the coordinates were just reversed. -2, 3 became 3, -2, -6, 0, 0, -6, and so on. So that's what we just saw in the warm-up. Y equals x was our line of reflection. Here we wanted to know which transformation. Well, notice it's oriented the same way. You got ACB as you go clockwise around. So this is just a slide or a shift. So all the points moved 5 to the left and 3 up because we went from the originals to the primes. So 2 ways we could notate it. We could do the capital T for translation, -5, 3, or you could draw it with a coordinate. So xy becomes x -5 and y +3. Either of those would be fine. For number 3, we used all of our spare grids for this one. So reflection through 0, 0, you're just counting to see how to get there and then repeat it again. So -3, 4. X-axis, you're just counting how far to get to the x-axis, repeat it. For the -6, 2. So there's -6, 2. we want to rotate this 90 degrees. It's positive 90, so we should be going counterclockwise. So that A should end up down in this quadrant in quadrant 3. So just turn your paper. So it looks like it's in quadrant 3 now. That coordinate now looks like -2, -6. That's how we can get our image. Translation in D, we're just subtracting 1 from the x, adding 5 to the y, so -4, 0. It's E you could have done just like you did A, but you are counting how to move to get to 1, -2, and then repeating it, so -2, -10. And then F was just like the warm-up, count how far to get to x equals -2, and repeat that again. For our constructions, line of reflections, pick 2 points that are in corresponding parts. I guess actually just one set of points you need. And do the perpendicular bisector. So I chose these 2 points here, connect them, and then just put point on one end point, pencil over halfway, swoop it in both directions, and do the same for the other side. Connect your intersections, and that gives you your line of reflection. For the center of rotation, we basically do what we just did for a line of reflection, but you have to do it twice. And where those two perpendicular bisectors intersect, that is your center of rotation. So notice this arrow here. Our pre-image to our image was going counterclockwise, so that would have been a positive degree rotation. In 6, let's kind of go through 6 because translations can be tricky sometimes. So I'm just going to show it for one of the 2 points, and then it would be the same for the other. So set your compass from A to B. And my compass doesn't allow me to get it exact, but yours should be able to get you right on that point. Now we basically know each of those points X and Y should go down into the right a little. So now put my point on X, make an arc that's down into the right. And then the distance from A to X should be the same as the distance from B to X prime. So I'll put my point on A, and I'm going to put my pencil on X. And again, my compass doesn't allow it to get perfect all the time. Yours should be able to. So now I'll put my point on B, and I'll make an arc. Now notice, sometimes if it's kind of close, it'll cross twice. So you have to think about which one is making it go down at the angle we want. So I'm just going to roughly sketch this quick, and then I'll erase them. So we have option 1 or option 2. We want to know which of those is going at the same slant and the same distance. Option 1 matches our vector AB there. So that's the one we would want. So this would be X prime. And then you do the same idea with Y. And there's the completed translation there. For 7, capital R, we have a rotation. The thing that's being rotated is triangle ABC, 45 degrees counterclockwise, and we're going around point A. Because it's a positive 45, if you just said 45 degrees, that would be fine as well, because that implies counterclockwise. Little r is a reflection. Capital X is a point, so we're reflecting that point over line N, and we know N is a line because it's a lowercase letter. If it was a point, it would be an uppercase letter. For 8, we're doing kind of like what we did in the second question. So you could either do a capital T, and if we're going 4 left, that would be a -4, and up 2 would be a +2. Or you could write explicitly what's happening to the point XY. You're subtracting 4 from the X and adding 2 to the Y. In B, reflections, little r. A is what's being reflected, so that's in the parentheses, and we're going through point B, so that is your subscript. All right, we're going to be starting on page 37. and today's topic is symmetries. So a line of symmetry is such that if the figure was reflected over that line, it would basically land on itself. Imagine if you were able to fold your piece of paper, and when you folded it, the figure folded over onto itself. The line of symmetry should be equidistant from all of those points that are landing on top of each other. So in this first one here, we're just going to freehand draw in our lines of symmetry. So in this one here, our line of symmetry would be right about there. If we were to fold it on that line, the figure would fold over onto itself. If we go down to the bottom, the first one there, assuming this is an isosceles right triangle, we would have a line of symmetry that would go from the right angle right through the midpoint. So that would cause the triangle to fold over on itself. In our rectangle here, we would have a vertical line of symmetry that would go through the midpoints of each side, and we'd have a horizontal line of symmetry as well. Now, a common misconception is that a rectangle has a diagonal line of symmetry. If you take one of the pages in your packet and you try to fold it along the diagonal, what you'll find is those corners that are kind of flipping over don't end up meeting up. And that shows that a rectangle does not have a diagonal line of symmetry. If we go over to the next page, in C, we've got a hexagon now. And there's two different ways we can draw in lines of symmetry here. We could draw in a line of symmetry that goes through the vertices, and that could cause the figure to fold over on itself. So we could draw in each of those. There's 3 of those types of lines of symmetry. But then we also could have a line of symmetry that goes through the midpoints of the sides. So we've got a vertical line of symmetry here, because that would cause the hexagon to fold over on itself from left to right, and you'd have that through each of the different midpoints of the sides. So notice all together there are 6 lines of symmetry. We've got the 3 green ones that go through the midpoints, and then the 3 purple ones that go through the vertices. In this next one here, we've got a diagonal line of symmetry going this way that would cause it to fold over on itself. And then we've also got a diagonal line of symmetry going the other way. So lines of symmetry are any lines that would cause the figure to fold over on itself. From a graph, often the lines of symmetry that we talk about are the axes, the x-axis and the y-axis. And when you get into Algebra 2, there's a connection about what are called even functions, and even functions have the y-axis as a line of symmetry. So this idea of symmetry will connect to functions next year when you're in Algebra 2. Our second type of symmetry today is rotational symmetry. Rotational symmetry is the number of degrees that you could spin a figure and have it look exactly the same as it started. Now, we do not consider 360 degrees to be rotational symmetry because everything could be rotated 360 degrees and look the same. So in this ellipse here, ellipse is just the fancy math name for what is often referred to as an oval in everyday language. You will work with ellipses in pre-calc a decent amount. So if I spin this ellipse, it is not yet looking like it originally did. Here's the first time it looks the same. So it took 2 turns, so that would mean it has 180 degrees rotational symmetry. If I keep spinning that, in relation to the original, here's 270, and then that's 360. We're back to where we started. So only 300 or only 180 degrees was our rotational symmetry. Now in this regular pentagon here, I can spin this and notice that now looks the same as what I started with. Well, how do we figure out what that rotational symmetry amount is? It wasn't a nice quarter turn or a half turn or anything like that. Well, the way we go about it is the regular pentagon has 5 congruent parts. Spinning all the way around would be 360. So what we do is we just take that 360 divided by those 5 congruent parts, and that means 72 degrees will be our smallest degree of rotational symmetry. So let's start by listing 72. But if I spin it another 72 degrees, that will also make it look the same as the original. So essentially, we're going to just keep adding 72 degrees on each time here. So we'll have 144 degrees. We'll have 216 degrees. And again, this is just by adding 72 each time. And then 288 degrees. If we added 72 again, that would take us right back to 360, which we don't do 360 as a degree of rotational symmetry because every figure you could spin at 360 and it would look the same. All right, if we go over to page 39, we're going to jump down to question C. So we're using the figure up above, which is an equilateral triangle, and we want to know what measure or measures does the equilateral triangle have a rotational symmetry. Well, just to recap, with the pentagon, we did 360 divided by 5 because there was 5 congruent parts to get that smallest degree of rotational symmetry, and then we just added that degree amount over and over again. So in this case, we're going to have 360. The equilateral triangle has 3 sets of congruent parts, so we'll divide by 3, so that'll give us 120 degrees. So 120 will be our first one. If we add on another 120, that'll give us 240 degrees. And if you add on another 120, that'll take us back to 360. And again, we don't include 360 because every figure has 360 degree rotational symmetry. So we don't include that. So in general, if you've got a regular polygon, which means all the sides and interior angles are congruent, how can you find that degree measure for the rotational symmetry? Well, we're just doing 360 divided by the number of sides. That'll give us that smallest degree of rotational symmetry, and then just keep adding that on. And then once we get to 360, we don't include that one, and that's when we know to stop. So we're going to pause the video for 2 minutes, see if you can do 5E, see if you can find all the degrees of rotational symmetry for this hexagon. So we wanted to do 360 divided by 60, or sorry, divided by 6 would give us 60. So 60 degrees is our first degree of rotational symmetry. Add on another 60, you get 120. Another 60 would give us 180. Another 60 would give us 240. And then another 60 would give us 300 degrees. If we did 60 from there, we would just get 360, so we're back to where we started. We're going to skip question 6A on page 40, and we're going to move to the bottom of page 40. And we'll look at our last type of symmetry for today, which is point symmetry. Point symmetry occurs when you spin the figure 180 degrees, and it looks identical to the original. So what I've done for each of these, we're just going to write yes or no underneath for whether or not they have point symmetry. And what I've done is I've put a carbon copy of the figure so I can spin it in red here, and we'll be able to see if it matches with the original. So again, your check is you're spinning at 180. At your seats, what you can do is you can just spin your packet upside down, and you can look to see which ones look exactly the same. I am not able to spin the smartboard upside down, so I've got to do individual figures. So that first one, notice I spun it upside down, looks exactly the same. So yes, this one would have point symmetry. The next one, when I spin it upside down, notice it is not identical, so that would not have point symmetry. E, when I spin it upside down, does not match up, so that does not have point symmetry. Our trapezoid, when I spin it upside down, it does not look the same, so that does not have point symmetry. Our Z, when we spin it upside down, looks like I maybe didn't have it matching perfectly, but the intent was for that one to land right on top of it and be the same. So that would be a yes. And this last one, the X, if we spin it upside down, it does land right on top of itself and look the same, so that would have point symmetry. Now, I mentioned before that in Algebra 2, you'll learn about even functions, and their graphs are symmetrical with the y-axis. You'll also learn about what are called odd functions in Algebra 2. Odd functions are symmetrical about the origin, and what that is if you spin them upside down and they look the same, then it'll be symmetric about the origin, because that's a point symmetry, because the origin is a point. So our three symmetries for today: line symmetry, if you fold it over that line and it lands on top of itself, then it has line symmetry. Rotational is if you spin it a certain number of degrees and the figure looks the same, that's your rotational symmetry. And then point symmetry is if when you spin it 180, or in other words upside down, if it looks the same, then that would be point symmetry. So over on page 41, we're just going to list of our three options, line, rotational, and point symmetry, what each of these figures would have. This oval or this ellipse has both vertical and horizontal line symmetry. So we could have split it like that or that, and it would fold over on itself. Rotational, if we spun that oval or ellipse upside down, it would look the same, so that would have rotational symmetry. Now they want us, if it does have rotational, to tell the smallest degree. Because we're spinning it upside down, that would be 180 degrees of rotational symmetry. And spinning at 180, if it looks the same, that's the definition of point symmetry. So this one would have the point symmetry as well. In B, we've got a horizontal line symmetry. If we were to spin this, we would need the rounded part to the left and kind of the cave type part to the right. And when you spin it, it would not be exactly the same until you got all the way back around. So there's no rotational or point symmetry. For C, the rectangle, we have both vertical and horizontal line symmetry. We have rotational. We could spin this 180 degrees. And then if you can spin 180, then it's got to have point symmetry, because that's just the definition of point symmetry when you spin it upside down. And I should mention, if it didn't have any of these symmetries, we would just say none. So for D, we could have several line symmetries. We could have vertical, horizontal, and we also got diagonal. So a whole bunch of line symmetries there. We would have rotational here, and here we would only have to do a quarter turn for it to look the same. So that would be 90-degree rotational symmetry. Well, if it's got 90 degree, it would have each multiple of 90, so 90, 180, 270. If it has 180, then that would be point symmetry, because that is when it looks the same if it's spun upside down. Alrighty, we're going to pause the video for a minute, and we're going to let you try the bottom four. Again, tell if it has line, rotational, or point symmetry. If it has none of them, just say none. And if it does happen to have rotational symmetry, tell what that smallest degree of rotational symmetry is. So again, we'll pause the video for a minute for you to do that. All right, first one, we have a vertical line of symmetry. That should be the only symmetry we have. For the lightning bolt there are no lines of symmetry. C here, this is basically a trapezoid because you have one pair of parallel sides. This should have been none. And the smiley face, you've got a vertical line of symmetry, but no rotational symmetry or point symmetries. All right, I just want to point one thing out on the homework before we let you get going. Oh, and one thing I wanted to point out as well. So back in the years of COVID, when we had cohort A, cohort B, cohort C, those things, um, we had my students were on video when we were teaching this lesson, and in the background of one of my students, they were watching the lesson in their kitchen. They had this clock, and I had them take a picture of it and send it to me because it was so nice for our lesson on symmetries. We've got rotational symmetry there. So if we spun this 90 degrees, 180 degrees, 270 degrees, and now I should say if we ignore the hands of the clock. If the hands of the clock there obviously wouldn't have the symmetries, but like the background of the clock, it does have those rotational symmetries. Because it has 180-degree rotational symmetry, it would also have point symmetry as well. So it just kind of happened that I saw that in their background on the day we were teaching this lesson, so I've included it in the notes in years since then. Okay, so on the homework, I just want to look at question 1. So 2 things I want to point out. Part B, you should be able to find that after you've done part A. When you draw in your lines of symmetry, where they're all crossing, that's just going to be your center of rotational symmetry. For part E, how many places can vertex A be moved by some symmetry of the pentagon? So what you want to think about is if there's any rotational symmetries, when you end up rotating it, what are the different locations that A could end up? And then if you have line symmetries, if you were to fold it over that line, what's a location that A could end up? So for example, spoiler alert, but there's a line of symmetry in this pentagon. If you folded it over that line, you would end up at point C. So C is one of the locations that A could be moved by some type of symmetry. So look at all your different line symmetries and all your different rotational symmetries and count up how many different places that A could end up. And then the last one for F, if we know the image of A, how many different symmetries could exist? And we're just going to do that one together. So let's say that A was going to end up at C. Well, what are the different symmetries that could cause A to go to C? Well, one of them is the one we just drew, a line symmetry. And then the other is, what if we rotated it? So we would have to go 1, 2, 3 rotations, and that could get you to C as well. So how many different possibilities are there? There's 2. You could have one of them from line symmetry and one from point symmetry. And that tends to be a tricky question, which is why I wanted us to do it together. Okay, any time left in the period, you can be working on this homework, and have a great rest of your day.